Today we have JPEG compression. Okay, JPEG.jpg is the most used image compression lossy technique. So it consists of a lot of steps. First of which is conversion from RGB to YCBCR color space. RGB is like a vector. You know that every pixel in color image has three color representation. For example, white will be 255, corresponding to the value of R, of G and B, and the black will be 0, 0, 0 respectively. So each color can be represented by some values inside this vector. We convert this representation into YCBCR representation, where Y corresponds to luma, brightness. It's kind of black and white image remnant, where Y corresponds to the brightness of the pixel, to how much each pixel will be white and black. And CB and CR give in their values to color the image, to ink it. So CB corresponds to some value inside blue to yellow interval, where 0 will be blue and 255 will be yellow, and here red cyan for CR. So Y corresponds to brightness, it's luma channel, and CB and CR correspond to chroma channels, which means color. And this is the formula for conversion. Second step of the JPEG is channel subsampling. It's a lossy step, and usually JPEG replaces 4 chroma values by 2x2 blocks with a single value. But also the algorithm supports other options. For example, you could use 4x4 blocks, etc. We apply this operation only to chroma channels. And yet another step of the JPEG is discrete cosine transform. It's the most important step. You can see the scary formula on the whiteboard, but we are not going to dig into this too much. So the intuition of this is that we represent our image in another basis. We abstract from the idea that image contains pixels at certain positions with some values, but we represent an image. We start thinking of an image in another way. We think of the changes on the image as periodic functions. This is the intuition. But at the end, we use the formula to transform our image into certain coefficients. And now the quantization step. We acquire some coefficients from the discrete cosine transform step. Coefficients correspond to the measure of how much our image on the 8x8 block has different frequencies there. Yeah. So to quantize these coefficients, we will use quantization matrix, which is also 8x8. Each coefficient from the previous step is quantized differently. The more the position of the coefficient is to the bottom and to the right, the more it is quantized, because in this matrix the coefficients which are here in this corner of the matrix, they represent the higher frequencies which our 8x8 blocks contain. They are not so important for human eye, because human perception functions in such a manner that we mostly care about forms and shapes and not the small details. So we divide each coefficients by the corresponding entry from the quantization matrix and round what we produced to the next integer. So 8x8 matrix, each element is divided by quantization matrix element, and we produce quantized coefficients. After we quantized our coefficients, we have to reorder them. That's needed for later encoding. So first, top left corner coefficient here, the very first coefficient, is called direct current. So we will later call it DC coefficient. It represents the average gray value of a block, 8x8 block. The remaining 63, because it's 8 by 8 like matrix, the remaining 63 are alternating current coefficients. Produced coefficients are now encoded with Huffman. Huffman trees are predefined in JPEG, but there are important things. Only the difference between successive DC coefficients is coded. That is, the next DC is predicted to be equal to the previous DC coefficient. Instead of directly storing the error of prediction, each error is assigned to a category. First category only contains 0, but each following category is twice as large as the previous one. Additional bits are used to indicate the exact number in the category. I will give now a table with the category and values, and you will understand what that means. Okay, this is a big table of categories and their codes and values, etc. If you don't understand why we use it, I will later give an example, and it will become very easy. And one useful addition here. We encode not only the category with these bits, but also the number in binary. If the number is less than 0, it can happen. Binary representation of a number has flipped bits. For example, if we've got 110, it will become 001 for negative number. This table only regards the DC coefficients. Now we will come to the AC coefficients. And this is the encoding table predefined in JPEG for AC coefficients. So, if we have how to determine which RL we have. Once we have determined that, we can use code word from the corresponding entry. We know that most of our AC coefficients are quantized very harsh, and thus there will be a lot of zeros produced. This number, this is here, determines the category, and the second number determines the number of consequent zeros in our code for AC coefficients. I will give the example now. To decode the example, you have to use this table and to encode too. So our example now. These are our reordered coefficients. We are going to encode them using two tables I have provided. Useful remarks here. 1010 is the code reserved for the end of the block, and this 8 ones, 2 zeros, 1, 1 indicates more than 15 zeros in a row. So, first of all, what we have to do is to understand that this is DC coefficient, right? To which category this number fits? It is inside 32 to 63, right? It's category 6 category, and we know the code for it, 1110. Also we have to store binary representation of 39, because what we store now is only the category we are in. So the binary code for 39 will be 10 100 111. Second step. Now we look at the number of consequent zeros here. Okay, this is only one consequent zero, and then minus 2. Okay, 0 minus 2, we encode it not separately, encode it together. We'll look at, this is AC coefficients, so we are ready that a lot of zeros will be here. We'll look at the category RL1 and category 2, because this refers to the second category, these numbers, and this refers to number of zeros, 10. So we'll look at the code. It is 11011 according to the table, and we have to use flipped binary representation of 2, because it's minus 2, it's negative 2. Flipped will be this one. So this is the code for this part. We continue encoding. Next is 1. It's AC coefficient. Run length is 0, because 0 zeros we have seen. And category 1, okay, just this code 001. according to the table. Just we have taken just the number from the table. Also, this is for, and this is binary representation of 1. Okay, then follows -1. Absolutely the same, but will produce 0 because it's flipped 1, right? Because it's negative number. Then comes 5th step. We see here 0, 0, 0, -1. It will be round length 3, category 1. 1, 1, 0, 1, 0, 0. And then we know this is the remaining zeros, just the remaining zeros. We will give them 1, 0, 1, 0 code, what refers to the code for end of the block. And that's it.